Guys, in this video I finally managed to implement DeepSeek's multi-head latent attention into my small open LLM and start the training from scratch. Here you can see I was training it on free Google Colab, so the whole LLM pre-training on a single GPU for free. So I had these steps. As you can see, it works well. There was a bug yesterday in yesterday's video, but we solved it today. Now there are some issues, but we will deal with that tomorrow. But the pre-training worked. I implemented DeepSeek's multi-head latent attention, and so you will learn the following things in this video. By the way, this is just a small test to see if the pre-training works. I have yet to do the full pre-training of my small model on these free Google Colab GPUs. So you can watch my videos to stay updated and to learn how to do it yourself and how to build on top of my project that was also done in collaboration with other people. In this video, you will learn how .backward function works, builds computational graphs, saves intermediary tensors for backpropagation. So you will just learn so much about a .backward function in PyTorch. You will learn why you shouldn't modify values in place, but instead create variables. If you don't know what this means, excellent, you will know what it means later in this video, and how to debug .backward. So we will use this function to find our bug and to solve it. And just as a fun fact, in future videos I plan to now benchmark this DeepSeek's MLA attention mechanism against the base model and see which ones are better, and to maybe come up with new ideas and improvements to this DeepSeek's MLA mechanism. And guys, this video is mainly for self-studying. There are a lot of difficult concepts here, so I intend this for you to watch this. Whenever you don't understand something, you ask ChatGPT, you study it yourself. So in the description below, you can find a lot of self-study materials, so we can learn together. Let's look at the backward pass and backpropagation. So I have this weird piece of code here, self.cprojection.weight.detach.0. So it's a weird piece of code. So it's in my LLM, where I'm programming this LLM to be very cheap and easy to train. Anybody can train it. So I'm getting this error, runtime error, trying to backward through the graph a second time or directly access saved tensors after they have been freed. So let's try to understand what's happening here. I will leave these materials for a self-study in the description below. So by solving this error in my LLM, we will learn a lot about backward pass. So this error usually happens when you call loss.backward more than once on the same computational graph without a retained graph equals true. Or during the backward pass, PyTorch tries to use intermediate tensors that were already discharged, freed from memory after the first backward pass. So what are these intermediate tensors? Intermediate tensors, also called saved tensors or activations, are the temporary results computed during the forward pass that PyTorch saves because they are needed later to compute gradients in the backward pass. If you don't know what any of this means, like gradients or backward pass, you can just ask the AI, because these are materials, you can use them for self-study. So I will learn what I don't know, but you can learn what you don't know here. When you call loss.backward, PyTorch starts backpropagating through the computation graph. To compute gradients using the chain rule, it needs the gradients of the output with respect to the intermediate values. Partial derivatives, partial gradients actually. So partial derivatives, all of them form a gradient or gradients, multiple gradients, with respect to the weights. So you can ask AI to explain this further if you don't understand it. The intermediate values themselves become, because it needs intermediate values themselves, because some backward functions like relu, dropout, etc. need to know what the input was. So we need to save the intermediate value as well. Let's see some examples of intermediate tensors. Torch.random n, so we create 4 elements, and it has this required gradients true. So y is x times 2, it's intermediate step, intermediate tensor, and then z is y.mean. And then if we call backward on z, here is what happens. Y is equal to x times 2. PyTorch saves x because it's needed to compute this derivative of y with respect to x. And then z is equal to y.mean. PyTorch saves y because it needs to compute derivative of z with respect to y. So derivative, how does z change when y changes, and derivatives. So you need these derivatives for backpropagation so you can update weights. So you want to know how the loss changes, how the prediction changes when you change different weights in the model. So then backward pass, when z.backward is called, PyTorch computes derivative of z with respect to y. So that's going to be 1 over n because it's mean. Okay, then maybe this is the derivative of this mean function. I could ask ChatGPT to explain this further, but I think that's just derivative of this mean function. Then it computes this other derivative. It's going to be 2 because it's derivative from x squared. No, sorry, 2 times x, not x. X times 2. So the derivative is 2. It needs y and x to do this. So it needs these intermediate tensors. So x and y are intermediate tensors. But it is a bit weird here because the derivative is just 2. You don't need x. But let's say if this was x squared, then you would need x. Okay, let's just suppose if this was x squared, you would need x. And yeah, ChatGPT just corrected itself. I asked it about this issue and it says you don't technically need to save x to compute that derivative. But it's designed, this PyTorch uses a general purpose dynamic computation graph, so it doesn't check in advance if maybe some variables will not need to be saved. It just saves all of them, as I'm understanding. So in PyTorch, y is equal to x times 2 creates a mul backward 0 node in the computation graph. So this mul backward 0 is used for backpropagation for this operation. This node knows how to compute dy over dx, but to do that it normally saves x, saves 2, the other inputs, so these 2 inputs, so it can compute the product rule. The product rule, so of the derivative, this is just the derivation rule here. A variable times constant is equal to constant, so the derivative of this. But even in this simple case, PyTorch still stores x and 2 as part of the saved context unless optimization kicks in. So, and this is our more complex example. So we have this just this tensor. This tensor has 2 and -1 as values. It's just an array. And then y is equal to x squared. And then z is y sum. And then z dot backward. So now we need to save x because the derivative of this operation is, or function is 2 times x. Optimization. Let's look at this. So we have this context dot save for backward. Each function in PyTorch defines a forward pass. It has context and the x variable, and backward pass. It has context and grad output. So context dot save for backward x. This will save x for the backward pass. And we have this x is equal to context dot save tensors. So in this context, we have all of these saved tensors, saved values of these tensors, and we can extract them later in the backward pass. Also, when intermediate tensors are freed, by default, right after the first backward, PyTorch deletes those saved tensors to free up memory. So z.backward uses saved tensors, for example x and y that we saved previously. But if you call it again, z.backward the same. Error, saved tensors have been freed, so no more saved tensors. If you want to reuse them, you must use z.backward and then retain graph equals true. Okay, now we return to the beginning, so those are the two reasons that we might get an error, because the intermediate tensors are freed from the memory, so that was the second reason. Or you call loss.backward more than once on the same computational graph without retain graph equals true, so that was the first reason. So let's now analyze our spicy line of code that we want to understand, that will help us understand how this all works and fix my bug in the LLM. So self.cProjection.weights or weight, this is a parameter tensor, likely an NN parameter from a layer casted linear. This is layer in my code. It's just a linear layer. It normally requires gradient is equal to true, so the values will be saved, so later gradients can be calculated and we can use backward pass. Now, if you don't know what a linear layer is, and this casted linear is just a linear layer, or NN parameters, you can either watch my video or you can ask ChatGPT or self-study this. Okay, let's see, detach. This creates a new tensor that shares data with the original but does not track gradients. Okay, this is interesting, important. So detach, new tensor, same data, but doesn't track gradients like this other one did. So this weight.detach.0, this is one of the ways you can initialize weights in the beginning of the training, in the initialization. So let's dive deeper. Does .detach create a new tensor? Answer, yes, it creates a new tensor object, a new view that shares the same underlying memory, data buffer, but does not track gradients. So if we have A is equal to torch.random, some tensor, and that requires gradient to true, and we have B is A.detach, then A and B are two separate Python tensors objects. But A.data pointer is equal to B.data pointer. They point to the same storage in the memory. So in the GPU, they point to the same storage. And the B dot requires gradient is equal to false here. So you can think of B as a read and write window into the same memory. So you can modify same memory, but detached from Autograd. So not saving gradients. Why use detach if we are going to zero it out anyways in init? So here it's in multi-layer perceptron module in my code. We have this init and we have our line of code that might be causing some problems, but we also want to understand it. So actually ChatGPT says here that because this is done in the init method, the model is not yet part of any computation graph. So it's even unnecessary to call detach. We can just remove it because, as I understand, because it's just initializing, there is no computation graph here at all. But look, it says with torch no grad. So it's still explicitly saying that we don't want it to have these grad things, gradients. So I guess you could use both of them, but you still need to explicitly say that you don't want these gradients things. Without complicating it too much, we just want to initialize all of the tensors with zeros, because when a layer like NN linear or your custom casted linear is constructed, PyTorch initializes the weight and bias tensors immediately using its default init like Kaiming or Xavier. So these weights already have some data. You're simply overwriting that with zeros via 0. So Probably this was contribution by this guy who said, well, this training will be better if we initialize these weights at 0. So why this should be safe usually? This initializing is just setting the constants, values of the constants, and doesn't involve any computation graphs. So normally this wouldn't affect loss backward, because we have a bug that says we're trying to call loss backward 2 times or on a free tensor or something. But I don't know yet where is the bug, because we only call it once, I believe. So there could be some issues. For example, case A, the line is accidentally called during the training. If for some reason this line gets re-executed during training, example, if init is rerun or a new module is being instantiated dynamically mid-training, it may break the computational graph. You do a forward pass. Before backward you run this line, it zeroes out a parameter outside of Autograd. Then you call .backward, and Autograd sees that the graph is broken or tensors are missing, because we call this line outside. So we call this line with zero out tensors, and then Autograd sees tensors are missing or zeroed out. But likelihood is low, unless the training loop creates new modules during training. So we'll check all of this. Let's just read the possible problems. Case B, torch compile, inductor is used. This is likely culprit. Here's why. PyTorch compilation basics. Actually, I think this is the problem, because that was also the bug we had in previous video with rope. So I think we will just fix it. But let's read. Torch compile traces your model and builds a fused optimized graph for speed. You can watch my video about this here in coding rope. So how PyTorch compiles 5x faster code, I explained this here. The compiler inductor tracks how tensors are used, including which tensors are parameters, intermediates, constants, etc. Why this line causes trouble? You create a detached tensor, then do an in-place write, 0 on it. The compiler may misinterpret the in-place change as modifying a non-parameter or lose track of the version history of the parameter. Then during backward, when it tries to use this weights intermediate activations, they are either missing, already discarded, so I guess intermediate representations, activations, because we are zeroing it, considered outdated due to version mismatch, or the compiler thinks the tensor has already used was already used for backward once due to earlier operations. So even though detach 0 is technically legal, it interacts poorly with compiled graphs. So there is other possible error, but let's just use this one instead. So this is the solution with torch no grad. So it tells PyTorch explicitly, I'm modifying a tensor's data, but don't track it for Autograd. It does not create a new detached view, it modifies the parameter directly. It's safe, works well with torch compile, avoids subtle issues with detached views and in-place operations. So I will comment out this line, and I'll do it like this, give some indents. The moment of truth. Is it rendering? Is it gonna show errors? Well, there is no errors yet until now. Oh god, okay, the same error. Okay, let's see where it happens. Maybe it happens at a different place now. Let's see. So I also disabled these torch compile lines. So I have these other torch compile commands as decorators, just a sec here, but I don't think these matter. So even if I disable this, there is still this error. So maybe the problem is not within generating these computation graphs in torch compile, but maybe the error is in the new code I added. So this code, multi-head latent attention, it's from DeepSeek inference. Now,
they are using it for inference. So maybe they are doing these in-place transformations or changes of tensors. But we cannot do it like this for training, because for training we cannot edit these tensors in place because we need them later. We cannot just change them. We need them later to calculate gradients. So that might be the issue. So KV cache and positional embedding encoding cache in your MLA module are NN buffers. You are modifying them in place during the forward pass. So we're gonna add this line of code to the beginning of our script, and it should point more specifically to the operation that caused the issue. So let's do that. So I will just go to the beginning and literally here, I think, and save. And it looks like now we have a lot more detailed explanation. So let me copy all of this. I will just paste it into my Gemini. Okay, Gemini, maybe it was able to help me. Let's see. So this is a different error and a very good clue. I guess this is the same error maybe. Yeah, I mean it's still log softmax backward 0. So I guess this is problem with the softmax function backward gradient thing. So the gradients computed during the backward pass of the log softmax operation, which is part of the cross entropy, are resulting in none, not a number. This almost always happens due to one of the following reasons in the forward pass. Zero probabilities, so if softmax output probabilities for the correct class, or for all classes if there are issues, become extremely close to zero. So in memory maybe they get rounded up to zero. Its logarithm log 0 will be negative infinity. During propagation, this can lead to none or infinite gradients. Also, extremely large logits can, positive or negative, can saturate the softmax, leading to some probabilities being numerically 0 or 1. So if softmax logits I is 0 for the target class I, then log of that number is minus infinity. If it's 1 and 0 for, okay, so if softmax logits I is 1 for the target class I and 0 for all other classes, then it's fine. But if the logits are so extreme that the softmax computation itself becomes unstable, it can lead to nones. And also if logit tensors already have none or infinity values, then these will propagate through the loss calculation and its gradient. So I now implemented this code that's gonna check if the values some values are too big, too small, this, that. So I ran that code by Gemini and I got this output. So I will paste this back into Gemini and let's see what it says. So I guess we have this ellipsis here, which we shouldn't have. Maybe we should just have it like this. So hard coding it like that. Let me try to do that. And now I fixed it. So now it worked. And now we had the next problem. So the next problem, our torch Autograd set detect anomaly true has done its job, pinpointed the problematic operation in the forward pass. Yes, let's go. So we are now discovering this problem. The in-place update to self-positional embedding sketch inside MLA forward is what's causing the trying to backward through the graph a second time error. Let's go, we found it out, and it makes sense because this is the new code that I added. And it was working before I added this code. So this is the problem. We are modifying this self PE cache in place, setting it equal to this KPE. So K had positional encoding squeeze 2. Later in the same forward pass, self PE cache is read from. Here we are using a self PE cache. So we are reading it there. This creates a situation where self-PE cache is both an intermediate result being written to and an input to subsequent operations within the same graph traversal. Autograd likely sees this copy slices operation modifying this PE cache, and this copy slices, it's explained here. Copy slices is an internal Autograd name for the operation that handles indexed assignment, like tensor slices is equal to values. So here, where we are assigning it, this value to that tensor. Then when it tries to backpropagate through the einsum that reads from self-PE cache, it might get confused about the version of self-PE cache or try to reprocess the copy slice node, leading to the backward a second time error. The saved tensors for the original state of self-PE cache, if any were needed, or for the copy slice operation itself, might have been cleared. And a similar issue likely exists for self-KV cache as well, because we are doing the same thing here, I believe. Okay, it looks like we fixed our issue. So now we have a different issue, which is good, which means, so now everything seems to be good. So we just had to add some local variables and do some adjustments for the training, mostly done by Gemini and the Claude 4. And now this works. So now I just updated it to fix the new error. So I gave it this typecasting to make it stay in bfloat 16, even if these outputs are float 32 from KV norm. So just managing types here. And now it's been running for quite a while, and we have all of these debuggings, prompts and stuff. I mean, things that are happening. So I'm guessing our training is working, which makes me very happy. Let's go, let's go, let's go. It's working, eh? I think it's working. And our training works. We implemented DeepSeek's multi-head latent attention to train our LLM, which is crazy that we were able to do that. I mean, I expected to learn how to do it, but now that I've done it, it feels kind of crazy.